Okay, so our last step now is to do the fourth part, which is find the critical points. So I'm just going to give myself a bit more room here. And just so I can see it, I'm going to recopy f at x here. You wouldn't have to do this on your sheet, but I'm just going to do it so I can see it. And now, of course, step 4, we're going to find the critical points. So we need to differentiate this and set it equal to 0. So obviously, differentiation here is going to be a little bit more complicated than the ones we did yesterday. We'll have to use the quotient rule here. So the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So the derivative of the top is 2x minus 1 times the bottom is just x minus 3 minus derivative of the bottom, which is just 1, and I'll write the 1 there even though it's not very exciting, times the top, x squared minus x minus 2 all over the bottom squared. And now we'll rainbow the top to make it a little bit easier to see. So rainbowing here is 2x squared minus 6x minus 1x. That's that rainbow. And then plus 3. And here it's minus, and I'm just going to minus everything. It's like rainbowing a minus 1. Because multiplying by 1 doesn't do anything, but you're going to have to subtract it. So you're going to minus x squared, and then this becomes a plus x and a plus 2 all over x minus 3 squared. Now, obviously I'm going to collect like terms in a moment, but remember the purpose of this is to set it equal to 0. So I'm going to set this equal to 0 and recognize that even though taking the derivative is kind of nasty, the next step is to set this equal to 0, and so I'm going to take this and bring it up and multiply it by 0, and it will disappear. So the math gets a little bit easier in that stage because we don't have this fraction anymore. Because when I multiply it by 0, it's just 0. So the left side is 0, and now I only need to worry about the top because the bottom's now gone. So I'm going to collect like terms. I've got 2x squared and a minus x squared is just x squared. And then I've got a minus 6x, a minus 1x, and a plus 1x, so that's minus 6x. And then a 3 and a 2 gets me a 5. So just like in the one in the warm-up, and I think this is the exact one in the warm-up if I remember correctly, I can factor this. Since it's quadratic, I got to figure out there's two answers, and it's two numbers that multiply to 5 and add to negative 6, so that's going to be x minus 5 and x minus 1, which is going to result in two answers, x equals 5 and x equals 1. So there are two critical points at x equals 5 and x equals 1. Each of those is just the x coordinate. We need the actual y coordinate. So for each of these, we're going to sub them in. So there is f at 5. We'll sub it back into the original, which remember is our blue one. So I'll just make sure I can see the blue there. And it'll be 5 squared minus 5 minus 2 all over 5 minus 3. And if you double check that, I think it's 18 on the top and 2 on the bottom, but we get 9. So that means there's a critical point at 5, 9. And then do the same stuff at 2, f at 1, or sorry, at 1. So we're going to sub in 1, so it'd be 1 squared minus 1 minus 2 all over 1 minus 3. So on the top, that looks like negative 2 over negative 2, so it's 1. And so I have a critical point at 1, 1. So if you need to pause here, just make sure everyone's caught up, you can. But now we're actually going to plot these on. So we have some new points. So we've got the point 1, 1. There it is. And we know that's a max. Oh, well, actually, we don't know whether it's a max or min. We're going to test it out. But it looks like it's going to be a max. and then we have a 0.59. So there's 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I had to guess, it looks like that's going to be a min. But I can't say for sure. I still have to do my table. But now at least I've got 2 more points that makes our sketch even more accurate. Okay, so the last part of step 4 then is to test to see if these critical points are actually maxes or mins. So we're going to make our table. And again, we're going to look from left to right. So the first one going from left to right is 1. So I'm going to go x is less than 1 is the first interval. And then I actually hit 1. And then I have that spot in the middle that goes from 1, which is the first critical point, to the next critical point at 5. So it's 1 is less than x, which is less than 5. Then I hit my next critical point, which in this case is 5. And then my last interval is the end, which is x greater than 5. Our first row is to investigate the derivative. And when we investigate the derivative, we'll know what the actual graph looks like. So again, I'll give you a second here. If you need to pause to copy the chart down, then feel free. And ask questions with any of your classmates as to make sure that I have those intervals correct. Now, remember, what I'm doing in this chart is not testing the original. I'm testing the derivative. So I'm going to go up a little bit. Now, this is an important spot here. So I'm investigating the derivative. And if we look, this step right here is the derivative. See all that? That's the derivative. Now, I've done some work to the top, but I was able to get rid of the bottom because it multiplied by 0. But when I'm actually looking at this, I got to consider that part of the derivative. But there's a catch. Notice that no matter what interval I put in here for x, it doesn't matter if x is positive or negative, and it doesn't matter what you do here, you're going to square it. And so the bottom is always going to be positive, regardless of the interval. So it doesn't matter where your critical values are in this, you'll notice the bottom is always squared. And so the bottom is always going to be positive. So technically, you could only look at the top. And we know that the top actually reduced to this. So what we're investigating is the derivative, which is x minus 5 times x minus 1. And then technically over the bottom, which is positive. But I don't even need to write that part because it's not going to influence my work. But that is the derivative that I'm going to investigate. And then I'll go off and plug some points in to find out if the slopes are negative, which would mean it's decreasing, positive, which means it's increasing, or 0, which means we're at a critical point. So we're going to investigate this then when we're doing our derivative test. So we pick a number that is less than 1, so I'll choose 0. When I put it in 0, 0 minus 5 is going to be negative. 0 minus 1 is going to be negative. Again, the bottom is positive, I don't care. We get a positive, which means for the first interval, it's increasing. When you put in a 1, of course, you're going to get 0, so that's normal. Now we'll choose something between 1 and 5, so something easy. I'm going to choose 2. 2 minus 5 is negative. 2 minus 1, though, is positive. And the bottom, I don't care. So it's negative and negative. Negative and positive is negative. And so the middle part's going down because the slopes are negative. And then again, when I put in the other critical point, I'm going to get a 0. Now I pick something greater than 5. So I'll choose 6. 6 minus 5 makes it positive. 6 minus 1 is still positive. Again, the bottom, I don't care. So it's positive, which means the slopes are increasing. And so now I can confirm what I had guessed already when doing the graph, that from at this point here, we see that it is decreasing before, increasing before, decreasing after, which means this must be a local max. And then the other part, when I'm looking at this spot here, I see it's decreasing before, increasing after, and so that means that this must be a local min. And so that information here is important for this point, which I know now for sure is a max, and this point, which is a min. And so when I go off and do my sketch, I have to recognize that the graph can't go below that second point or above the other one. So I've done all my algebra, I've done all my algorithms. Remember, I'm skipping the step about concavity and points of inflection or anything like that. There aren't any in this. And so now we're going to go off and actually connect the dots, take all this information, and get a little bit more accurate graph than we did last semester. So it approaches this asymptote here, it comes up, and then I'm careful to make sure that that's a max, so it's as high as I go. And then I go down like this. And then the graph over here, I'm going to start at my min to make sure that I don't get any lower than that. I have it going that way and then coming up. And I get a shape like that. And so all of this work here are all of the steps necessary now to do our sketch. We find our vertical asymptotes, do limit tests, horizontal or oblique asymptotes, in which we might have to divide to get the directrix to do our limit tests, x and y intercepts as per usual, and then our new step, the first derivative test, where we differentiate, set it equal to 0 to find critical points. In this case, 5 and 1. We took those, sub in to find those actual coordinates. And then we do our table where we investigate the derivative and determine if those critical points are maxes and mins. Take all that together and we have our graph. And so now I'd like you to try all of these steps to sketch these. So there's 6 of them here to try. Some of them will just be boring old break your ankle graphs. We just have some vertical asymptotes, horizontal asymptote maybe. But you'll have to do all the steps for each of these graphs. So it'd be best if you can get at least 2 or 3 of these done today. We can take up some of them tomorrow, and then we'll finish sketching the rest tomorrow. Thanks, and we'll see you later.